Okay, so Hannah, I'll let you take things over.
So, first of all, many thanks for giving me opportunity to present this talk. I'm really honored and happy to be able to talk here. And happy birthday for you. 100 years of further life in good health and uh, productive mathematics. This work was done together with Robert Ovcharek, and this is topological invariant of manifolds and discussing a gauge choice.
Yeah, it's blocked.
The main points of this talk is in the first part, it will be introduction from the literature, because there are two fundamental fundamental blocks on which this research is built. It is, first of all, Witten's program of topological invariance, and we remind it quickly on the example of Chern-Simons theory, and then the classical formulation of Slawianowski's theory, which is in a sense complementary to this program. Then we defined a new invariant of n-dimensional manifold, which is analogous to Witten's invariant, provide definition and show what this invariant distinguishes. And in the last part, there's the newest part of our research, dealing with path integrals involving action that is a square root. And again, back to the literature, how the quantized gauge fields, how people are dealing with such action and proposition of our gauge choice. So the fundamental philosophy on which all this research is built was formulated by Professor Edward Witten in his absolutely fundamental paper, Quantum Field Theory and the Jones Polynomial. And he said, we want to formulate a generally covariant theory in which on all observables will be topological invariants. And to this aim, we want to pick a Lagrangian which does not require any choice of metric. This is the fundament, this is the philosophy of this whole research. And we are going into this in this program. This was the same paper that described Jones polynomial in terms of 3D quantum field theory. And as the example which was discussed, it was Chern-Simons Lagrangian. So this definition of the Jones polynomial was already discussed during the conference. This is just to refresh and remind that for manifold, which is three-dimensional sphere and group SU2, where Ri are the fundamental representation of SU2, the integral WRI is equivalent to the Jones polynomial. So this is the connection. A gauge field is defined there as a connection on principal G-bundle. It is a one form with values in the algebra of a semi-simple Lie group G. I'm stressing this because there will be parallel in the further research. The action called Lagrangian by Witten for this connection is as follows. This is about nomenclature. Unfortunately, the literature is not quite clear, and in some papers, what is called by Witten as Lagrangian is called action. So I would use both names, and please just understand whichever you are used to. This action, it means Lagrangian S, does not use any metric on the manifold M, only the smooth structure of M as required for the construction of topological invariant. The topological invariant proposed in this paper is connected to several known topological invariants of manifold, and it was shown on examples in written paper as follows. Now, let me go back to probably much less known Slawianowski's field theory, which also does not require any choice of metric. And it is defined on an n-dimensional manifold M using only the smooth structure of this manifold. Repair and field and its dual co-repair fields are sections of the principal bundle, GL and R, frame, and repair fields are defined in each point of the manifold, and the co-repair one forms are introduced such that repair and co-repair are dual by duality between vectors and covectors. Local repair and co-repair fields over a smooth manifold together with a flat teleparallelism connection are the building blocks of this theory. Action, it means Lagrangian in the Slawianowski. Action of the group on the frame bundle is given by right multiplication by the matrices, and family of the second order covariant tensors is defined using only dual fields of repairs and co-repairs. We have a definition of torsion for the flat teleparallelism connection. The curvature is 0. The action is defined as integral of connection scalar density over the manifold. And I want to stress that metric has not appeared yet. Everything is constructed without metric. Now let me go to some observations or philosophy of Slawianowski theory. He believed that in mathematics they are natural, you could call it canonical objects. So in this theory, Lie groups and semi-simple Lie groups appear as natural solutions in diverse applications of Slawianowski's field theory, from the theory of relativity to the description of defects in continuous media. And this was actually applying this formalism put a new light and new interpretation on some problems in continuous media, in field theories, because it stressed the importance of symmetry, and especially the importance that Lie groups and semi-simple Lie groups play in multiple examples of physical applications. The other thing is that Slawianowski believed that any space possesses its natural canonical metrics, and so that introducing a matrix before formulating a theory is premature, because it restricts our theory. The theory should reflect the natural properties of the manifold, and those properties manifest themselves also by the fact that one metric would be more natural than any others. The analogy is our matrices. A matrix can be written in many different bases, yet its natural basis is built of the eigenvalues of this matrix, eigenvectors, and provides eigenvalues for this matrix. And this is where we usually like to make all the calculations. We can do it in any other other basis, and we can use other than natural metrics on a manifold, but the computations would be much more difficult, and the symmetries of the manifold would not be as clearly visible. For some spaces and theories, the natural metric is known, it is obvious. Slawianowski believed, and I myself might say that I believe too, despite that I have no proof, that other spaces also possess those natural matrices, and even if they have not been found yet, they will be found. If we are dealing with general, not Lie group manifolds, the tensor gamma defined in the here in this tensor gamma is rather complicated, difficult to compute and to physically interpret. Difficult but not impossible. And actually, the last part of this talk is dealing with such general manifolds. So let us come back to the Lie group manifolds. Then the tensor gamma becomes the Cartan-Killing metric. And this is a definition. And the Cartan-Killing metric is a natural matrix on the Lie group manifolds in Slawianowski theory. This metric appeared here as a result. It is not an assumption of the theory. So in a sense, we have both good things together. It means we didn't assume any metric. On the other hand, the metric conveniently appeared, and we are able to use it and to define objects like what is parallel or what is perpendicular in this metric. So after this literature introduction, let us go to the new Witten type invariant on n-dimensional manifold, and we built it with the Lagrangian that didn't have any choice of metrics. After building this and trying to use, Robert and I decided that it is computationally beneficial to slightly modify this definition. We normalize it by the anyway unknown measure dE. This this normalization helps, especially for Lie groups. It makes the invariant computable. Still, let us ask, what is this invariant? What does it distinguish, and how it is related to the other invariants? So let us start from the easiest observations on the invariant. For general, not Lie group manifolds, the tensor gamma is a polynomial homogeneous in reper, coreper, and their first derivatives. And when even for three-dimensional manifold, if you write it explicitly, it is ugly, but not untractable. For Lie group manifolds, the tensor gamma becomes the Cartan-Killing metric. Appearance of the natural matrix allows interpreting the action as the volume of group manifold M. The Cartan-Killing matrix is degenerate for non-semisimple Lie group manifolds, so volume integral is 0 for those manifolds. So Z is we can compute Z, and it is equal to 0.
1.
To 1. Yes. Yes, because the thing under the square root is 0. For non-compact semisimple Lie group manifold, the metric is not defined, and the volume is in general is infinite. For compact semisimple group, the metric is defined, and the volume is finite. For example, for SU2, it is the volume of 3D sphere. So what this invariant distinguishes? Lie group manifolds against general manifolds, semisimple Lie groups against other Lie groups, compact semisimple Lie groups against non-compact ones, compact semisimple Lie groups against each other. And we also go to general manifolds, which are not Lie groups, and here the gauge choices play crucial role in interpretation. So now let us come back to literature and observation on quantizing gauge fields, which are path integrals involved. A general covariance of a theory leads to a square root from its Lagrangian. The square root type Lagrangian makes quantitative calculation within the theory extremely challenging. Theories with extensive symmetries have a lot of redundant degrees of freedom. Let us consider an example which is well known, at least in physics. Electromagnetic field in classical Maxwell theory in Minkowski space. So we can use formalism of electric field and magnetic field as 3D vector field and 3D pseudo-vector field, or we can use a 4D potential A mu with gauge freedom, and then electromagnetic field in this language is a gauge independent tensor. From tensor F we can build fields E and B. This is literature. This is still literature, and quantization of theory concerns the real degrees of freedom and requires a gauge choice breaking the theory's gauge invariance. And the two popular gauge choices used for electromagnetism is Lorentz gauge and Coulomb gauge. Both are breaking, and Coulomb gauge, both are breaking the gauge invariance, and Coulomb gauge additionally breaks Lorentz invariance too. So in quantizing the electromagnetic field, the gauge choices are dictated by computational convenience rather than by preservation of the symmetries intrinsic to the classical theory. And I want to say that by convenience, I don't mean that somebody was lazy. I mean that putting theory in a form in which any computations are really possible. So we are coming to our research and propose gauge choice in quantum field theory related to the classical Slawianowski theory. We use analogy with quantizing electromagnetism and make a choice of using some of the diffeomorphism invariance to free the theory from the irrational square root form of its Lagrangian, because this square root is really stops any practical computations. Of course, it was possible to compute even the invariant for Lie groups, but this is very special case because all those coefficients were constant, and whenever we are going out of Lie groups and consider the general case, square root form of Lagrange is stopping practically anything. This is under square root, there is a polynomial of homogeneous in Reper, co-Reper, and the first derivative. And I considered printing the Lagrangian for 3 dimensions, but those are multiple pages which would not be readable. And for 4 dimensions, this is difficult even to see on the computer. There are some gauging for which this Lagrangian becomes 0, and it will be investigated if those gauges for not Lie group solutions for which Lagrangian become 0 have anything in common with each other or not. At this moment, it is open. But let us come to not degenerated case. We divide the polynomial under the square root into 2 components. One that is a square or power of 4 of a polynomial, and it is still homogeneous in Reper, co-Reper, and the first derivatives. And the second part of the Lagrangian are all the other terms which we are asking to vanish under the gauge choice, and the gauge choice is actually to make them vanish. In this way, we obtain square root of a square of polynomial, and then we get absolute value of this polynomial, simplifying the action to a rational one. So such gauge choices provide a polynomial from form of the Lagrangian and allow in principle to explicitly compute the integral. Of course, all those computations are not doable by hand. This was done by symbolic calculations in Mathematica. The path after making it rational, the path integral in defining the invariant is rational in place of the previous irrational, still not second order or a perturbation of a second order polynomial. Those we still have difficulties. So we tried and obtained several gauge choices both in 3D and 4D. Only one is selected to be shown here, the simplest one. Others are analogous. It is just that they are written in much longer way, and it would not be well visible during a talk. The gauge and the resulting polynomial are expressed in terms of the repair and co-repair field. The gauge is described in the following way. This is the shortest and clearest gauge that I was able to find, and it is only for 3D. But there are many other gauges also in 4D. They are just more complicated. So, after imposing this gauge, we get a Lagrangian, which is square root of a square, actually with minus, but this minus really doesn't matter because this is absolute value, of a square of a polynomial. And this polynomial is also very, very long, so only the first term is written here. So this is the result. This is where Robert and we are on this at this moment. Let me go to the summary. This is summary of literature on which we built this research. Witten proposed topological invariance of manifolds defined by integrals over action depending exclusively on smooth structures of the manifold without any metrics. Example of Witten's construction is given in Chern-Simons theory on 3D manifolds. Slawianowski theory, and we are staying inside his program, and Slawianowski's theory is built without any use of metric, using frame-coframe field. So we defined a new Witten type topological invariant in any dimension using an integral over Slawianowski's repair fields. We applied in node, and actually we shown that it distinguishes Lie group manifolds and different types of Lie group manifolds distinguish against each other. We apply in general case, not Lie groups, we apply in low-dimensional gauges that means choices of repairs, frames that break general covariance, or in other words, diffeomorphism invariance, in order to remove irrationality in the form of square root in the Lagrangian, leaving polynomial Lagrangian in those cases. Though still not calculable as a path integral, it gives more hopes for physical analysis of such systems. Honesty meaning of this new invariant is not fully understood yet, and interpretation of any new invariant and its relation to the existing invariants is challenging. And we would be very happy to collaborate with any of you, estimable mathematician colleagues, if you would like to join us in this research. Thank you. This is bibliography. Those are papers which are the most important basis of the presented research. Thank you.
Great. Thank you very much. Thank you for the nice talk. Very nice. So let me stop the recording.